In the previous lesson, when we discussed similar figures, we always talked about the ratios that involve the corresponding sides of those figures. Today we're going to extend that discussion to include ratios of their perimeters, ratios of their areas, and ratios of their volumes. I'm going to start out by taking a look at two squares. We're going to take a look at one square whose sides have length of 2, and then a second square whose sides have length of 3. So I'm going to go ahead and draw a sketch of each of those figures. So there's my square whose sides each have a length of 2. And there's my square whose sides have a length of 3. Since by the title I know we're going to be talking about perimeters and areas also, I'm going to go find the perimeter of each one of those. Perimeter of the little guy would be all 4 of its sides added together, or 8. Perimeter of the big one, again, all its sides added together, or 12. And also I'm going to find their areas. Area of this little guy is going to be 2 times 2, which is 4, whereas the area of the larger square is going to be 3 times 3, or 9. The first thing they want us to do is explain why the squares must be similar. Well, I could explain this a couple of different ways. I could take, for instance, a sequence of similarity transformations that will map one onto the other. In other words, I could translate along the vector that'll map that blue vertex onto the blue vertex in the larger square. And then I could dilate using a scale factor of 3/2, which will superimpose or map the smaller square onto the larger one, making them similar to each other. The other thing I can say is I can say that all of their corresponding angles are congruent because they're all right angles, and all of their side lengths are in proportion. So whatever way you want to think about it, you can think about it in terms of similarity transformations. You can also think about it in terms of congruent angles and sides that are in proportion. But I'm going to jump ahead to letter B because this is really what the crux of our discussion is about today. It wants to know what is the ratio of their corresponding sides. And I can do this a couple different ways. I can compare the bigger one to the smaller one. I can compare the smaller one to the bigger one. If I write their ratio in comparing the smaller to the larger, the comparison between their two corresponding sides is going to be 2 to 3. But again, if you want to think about it comparing the larger to the small, 3 to 2 would be also acceptable. What is the ratio of their perimeters? Well, if I compare their perimeters, and again, just to be consistent with what I did here in part B, I'm going to start out by comparing smaller to larger. 8 is to 12, which when I simplify or reduce that, and this is the reason that we always simplify or reduce all of our ratios, I'm going to divide each of those by 4. So 8 divided by 4 gives me 2. 12 divided by 4 gives me 3, and voila, one of the big key ideas for today. Notice that the ratio of the perimeters and the ratio of the corresponding sides are exactly identical. If we know what the ratio of the perimeters is for any similar polygons, we also know the ratio of the corresponding sides, or vice versa. If they tell us one, we automatically know the other. So I'm going to use a little shorthand notation here and say the ratio of the perimeters is always going to be equal to the ratio of their corresponding sides. That's a big key idea. The next question wants to know what is the ratio of their areas. So I'm going to go ahead and compare smaller to larger. If I compare the area of the small one, 4 to the area of the large one, 9. I've written that now as 4 is to 9. And the big question here is, how does this area, or how does this ratio compare or relate to the ratio between their sides? Well, if we go back and look at the ratio between the sides, the ratio between the pairs of corresponding sides was 2 to 3. The ratio between their areas, 4 to 9. So a quick question then, how do we get from ratio of the sides to ratio of the areas? Well, notice that that ratio of the areas is the result that we get when we take the ratio of the sides and square it. So that too is a big key idea here. The ratio of the areas is always going to be what I get when I take the ratio of the sides and square it. Now you might be saying to yourself, oh my goodness, how am I going to remember this? Well, remember that area is always measured in square units. And that's my little trick for remembering. Since area is always measured in square units, in order to find the ratio between their areas, I'm going to take the ratio between any two corresponding sides and square it. That too is a really big key idea for this lesson. That's something you need to know. All right, let's go ahead and take this to the next level. We're going to build two cubes now using these same squares as faces. So if I build my first cube, and I'm not real terrific at drawing this, so if I can do it, you can probably do this much better. My first square had sides of length 2. My second square was a little bit bigger, and mine looked more like rectangular prisms than cubes. Just goes to show you don't have to be a good artist in order to do math. So it now wants us to compare their volumes. Well, the volume of the little cube is going to be 2 times 2 times 2, making that total volume 8. For the larger cube, volume will be 3 times 3 times 3, or in other words, 27. So now it wants us to go find the ratio between these two volumes. Well, if I compare the smaller one, 8, to the larger, 27, my ratio is going to be 8 to 27. And again, they want us to figure out the relationship between the ratio of the sides and that ratio that we found for the volumes. So in other words, what is the relationship between those two numbers? Well, if I take the 2 and I cube it, I end up with 8. Take the 3 and cube it, I end up with 27. So the big key idea here is that to find the ratio between the two volumes, you're going to take the ratio between any two corresponding sides, and you're going to cube it. And again, this I remember because volume is always measured in cubic units. Cubic inches, cubic centimeters, some kind of cubic units. And that's how I remember that in order to find the ratio of the volumes, I take the ratio of the sides and I cube it. All right, so down at the bottom, just in summary, for any two similar figures, explain how you would find the ratio of the perimeters. Well, the ratio of the perimeters is going to be the same as the ratio of the sides. Or in other words, the ratio of the perimeters is always equal to the ratio between any two corresponding sides. Explain how you would find the ratio of the areas. Well, again, area is measured in square units. So I would take the ratio of the sides and square it. So using my little shorthand notation here, the ratio of the areas is always going to be what you get when you take the ratio between any two corresponding sides and square it. And then lastly, determine the ratio of the volumes. Well, again, volume is always measured in cubic units. So I would take the ratio between the sides and cube it. So in other words, using my little shorthand notation to find the ratio of their volumes, take the ratio of their sides and cube it, or raise it to the third power. All right, so down at the bottom of page 12, that's a very nice summary of everything that you need to know and remember from this video. Up at the top of the page 13, I'm asking you to, again, summarize the key ideas, put down on your paper the important understandings, and then you can go ahead and see if you're able to apply what you've learned in those questions, numbers 2 through 6 down at the bottom. We'll check your answers when you come back to class and make sure that everybody's on the same page before we head on to the classwork dealing with this subject.